So are there any questions on what we did last time? Very good. Now last time I defined superspace. I showed you that supersymmetry is a transformation on superspace in which the anti-commuting coordinates are shifted by translation and the commuting ones are shifted by a piece depending on the anti-commuting ones. I hope you remember the form of that. Okay. It's more important to just remember roughly what the form was rather than check out the expression in detail, which you can do only when you need it. Theta goes to theta plus epsilon, but x goes to something involving epsilon sigma mu theta. That's the key point. Okay. Now then, what we said was that in terms of superspace, we can write a superfield, and we simply assume it to be a general function of all of superspace. So x mu, theta, and theta dagger. Theta has two complex components, and theta dagger are its complex components. And the dotted and undotted indices are not there explicit. Okay. And so we wrote that this is the most general. We wrote down this most general thing, and we noticed that if you expand it in powers of theta and theta dagger as if it was a Taylor expansion, then you get a few terms and then it terminates. The reason is the thetas are anti-commuting coordinates, and therefore at some point when you have enough of them, when you have all of them, let's say, which in this case are 4 independent objects, theta 1, theta 2, theta dagger 1 dot, theta 2 dagger, theta 2 dot dagger. When you have all 4 of them, then that's all you can have, and if you put a fifth one, then you will get 0. Okay, so the expansion of this thing in thetas terminates at 4th order. Okay, now that's means that when we carry out the expansion, the coefficient of each order in theta is a function just of x, because what we are doing is we are not expanding around any point in x, only about theta, and therefore we find finitely many functions of x are encoded in f. Function of x is the same as an ordinary field. Function of x, theta, theta dagger is a superfield. So we learn that a superfield is nothing but a package which encodes a finite number of ordinary fields. Okay. And in fact, so this implies that superfield just packages a finite number of ordinary fields. And just to remind ourselves, I'll write down again what I wrote last time. It's a little ugly and wrong, but it's worth seeing a few times. So there it is. And although it looks a little bit complicated, I want to just point out a few features of this expansion of a general superfield. The first thing is, by our choice, we didn't assign any index to this f. In principle, it could itself have been something like a vector or a spinor or something. We just chose it to be a scalar, so it's a scalar superfield, and we'll get by pretty well most of the time with scalar superfields. Yes, 10, sure. It being a scalar, all its components are scalars. Okay, but the first one, since it occurs all by itself, is an ordinary scalar field. Here what we have instead is that theta psi is a scalar, but since theta is a spinor, it follows that psi is a spinor. Okay, so everybody in this gets their transformation properties by what function of theta they multiply. One of the most interesting surely is this one, which is theta sigma mu theta dagger times a mu. I've labeled it a mu for the obvious reason. It's inherited a vector index because it's contracting something with a vector index. Okay, and this is a vector field, and so we should certainly expect that in this package, this is actually a normal scalar field, this is a spinor field, this is a vector field, and so on.
Tensor fields excluded from this?
Yeah, so that's a good question. Tensor fields are excluded from this because of our choice of having one two-component theta and its conjugate, because this is the most general expansion there is in two thetas and two theta daggers. Okay. Now you may say nothing actually stops you having some contraction, some term. So why didn't we have? It's a good question. But I was meaning to say this. Why didn't we have a term like theta sigma mu theta dagger, which is allowed? Theta sigma nu theta dagger times some tensor field mu of x. Okay. So who knows the answer to that? Supersymmetry n equals 1 is not an answer to this question. Supersymmetry n equals 1 is what we are doing. The question is, when I expanded a general superfield as a function of theta and theta dagger, why didn't I find a term like this? It's symmetric in what? There are two thetas and two theta bars, that's fine. So it's not 0. No, it's not 0 if that's what you're saying, because you have to look at the contractions. So this is theta sigma theta dagger, theta sigma nu theta dagger. When you just see a theta, it doesn't mean it's just a theta. It means it's both the components of theta. So if all goes well, there will be a term here with theta 1 occurring and here with theta 2 occurring. So we'll be fine. And in fact, it is not 0, that I can tell you already. So the question is, why didn't it appear in this general expansion of a general superfield over these two coordinates, theta and theta dagger? Come on, people from other institutes are watching you. It's not antisymmetric, it's manifestly symmetric in mu and u. And if it was antisymmetric, so what? Then we'd have said that this is an antisymmetric tensor field. That wouldn't have killed us. But actually it's symmetric. Next. People have not been working out the details of this thing.
The Taylor expansion cannot have this term.
Why not?
Because
it's an expansion. Why did it have theta sigma mu theta dagger? Right? If it can have one term, it can certainly have the square of that term, unless for some reason it's 0, but I'm telling you that it's not 0. So it's there. So why didn't I write it in this? Somebody except Shiraz? Okay, Shiraz.
Sorry, the question is, I'm sorry, can you tell me how many?
Just before you came in, what happened was, we said this is the most general superfield as a function of theta and theta bar.
But in 4 it doesn't matter.
In 4 dimensions. We have only in 4 dimensions n equals 1. We are not doing it. So I expanded it and I claimed this is the expansion. And last time, at the end of the lecture, I pointed out
there are two theta stars.
There are two theta stars. These contractions are actually with some dotted indices. I explained in an earlier lecture exactly how it's done. Okay, and I pointed out last time that if you count up components, then of course the bosons are the ones multiplying even number of theta. So phi, m, n, a mu, and p, and those together have 8 complex components, and the fermions also have 8 complex components. So it looks good. And I did a fair amount of theta and sigma mu algebra already.
You want to know why that.
And I want to know why I could get why my claim that this is correct, that this is the full expansion, why that claim is correct, given that there is such a term, because Asim in fact asked how come I don't have any tensor fields in this expansion, and this looks like I would have a tensor field.
But there's a unique term with 4 thetas.
That's the answer. Okay. The answer is that this term is there, however this happens to be equal to theta theta, theta dagger, eta mu mu with a factor of half. This is actually an identity. Okay. It's an almost obvious identity because both of them having 4 thetas must be proportional. So let's see the proof. By both terms I mean this one which looks like a tensor and this one which is actually a scalar tensor, simple tensor eta mu mu. Both terms are proportional to theta 1, theta 2, theta dagger 1 dot, theta dagger dot. Okay, because they have 4 thetas and the only term in 4 thetas that can be there, however you may want to package it, has to be the product of all the 4 thetas. So there is no other function of that is 4th power in theta other than that. Okay, therefore both must be proportional to this. Okay, however this one being a second rank tensor in mu and mu, but being proportional to this and therefore to this must be multiplied by a constant tensor, and the only constant tensor theta mu, and that the only thing left is to find the factor. I'll be using this formula in a moment, but I think it does show us that invariants that you can form from thetas are slightly subtle, and you need to get some experience about what invariants exist and what don't. I made the point last time that I hope you remember that theta sigma mu nu theta was another possible invariant, and this time it was 0. And why was it 0? You can check that in my basis sigma mu nu is a definite matrix, right? And you can check that that matrix has a symmetry property which makes this 0. Okay, you have to be a little careful. This has got one lower and one upper index. This is upper, this is lower. When you do everything and keep in mind that theta is anticommute, then you will find that the terms you get by expanding out this thing all cancel out, and this is 0. So here's another possible tensor that would have occurred but didn't. Okay, so we see that we'll never ever with this many thetas get more fields than these. So if there's going to be any supersymmetry with supersymmetric theory with more fields than these, we are going to find it within the limitations of our study, which is 1 2-component theta. This goes by the name of n equals 1 supersymmetry, and it's the only case relevant to studying the standard model, supersymmetric standard model. Okay. Later on in the course, this is not going to be a formally oriented course. I want to get to the phenomenological model soon, but it's quite an easy theorem to prove that n equals 2 supersymmetry onwards, which would have had a larger superspace with more thetas, has properties which are immediately at variance with low energy properties of the world. For one thing, it doesn't admit parity violation. So we'd never be able to write a Lagrangian in which we had left-handed doublets and right-handed singlets if there was n equals 2 supersymmetry. So we are only working in n equals 1. Good. Okay. Now this superfield is rather long and messy, and moreover this is a good reason why it's got too much information for us, because last time I wrote down for you 2 actions, one involving a scalar and a fermion, one involving a vector field and a fermion, both of which I claimed had supersymmetry, okay, but both of which had a very limited field content. In one case there was just a complex scalar and a fermion, and in the other case there was just a vector field and a fermion. There was nothing else, and I showed that there are some free actions which are supersymmetric. And so the puzzle is, how come this superfield with 8 complex bosons and 8 complex fermions reproduces that kind of system? And the answer is, this is the most general superfield, so it's a good idea to look for possible constraints I can impose to make the superfield simpler and have a smaller content. Now, right off, the first constraint that comes to mind is, well, the superfield depends on theta and theta dagger. Okay, but these are complex conjugates of each other. So, could I not consider something like an analytic superfield, which depends only on theta and not theta dagger? Analytic or holomorphic. This depends on one and not the other component. Okay, we would like to imagine, as it turns out, the situation is a little more complicated. An analytic superfield F, which depends on x and theta, independent of theta dagger. So this would have to satisfy such a statement that we have a function of x and theta independent of theta dagger would have to satisfy the constraint del by del theta dagger a dot on f equals 0. Okay, it's the same statement. If del by del theta dagger on f is 0, then it is a function of x and theta only. Okay, of course f is complex, so under this condition f would depend on x and theta, while f dagger, its own complex conjugate, would depend on x and theta dagger. Everything would make sense. Let's make a quick inspection of this formula and figure out how many terms disappear when theta dagger dependence is removed. Okay, most of them. Any term involving theta dagger would instantly disappear from a superfield obeying this constraint. You see that? So how many terms would be left? This one, and that one, and that's it. So that looks very good. So under this assumption, under this constraint, we would have f equals phi plus root 2 theta psi plus theta theta, some field. Can we, what we call it doesn't matter, but I'll keep calling it m for now. So it would be much simpler. Moreover, it's suspiciously similar to the system we considered last time in ordinary space, because we considered a system of a scalar field and a spinor field and nothing else. And here we've got pretty close because we have a scalar field, a spinor field, and one more thing, which hopefully we can do something about. Okay, so it's pretty close. However, this prescription turns out to be too naive. Because, does anyone know the reason already? What about auxiliary field?
I mean, it depends on the equation.
I'm claiming that this prescription to define a superfield constrained by this lack of dependence on theta dagger is too naive for us to use because of a very important property of superspace, which is the supersymmetry transformation on that space.
That's
okay. Sorry?
Transformations of x will depend on theta.
That's correct. The transformations of x depend on theta and theta dagger. Or a simpler way of saying it is that f, the superfield, transforms by, we've seen this last time, by epsilon q plus epsilon dagger q dagger f. This is the infinitesimal transformation of a superfield in superspace. Okay, is the strict analog of a transformation of an ordinary field under translation. And it is a translation because if you remember what Q was, Q is basically a translation operator along different directions of superspace. But slightly different from a translation operator, but very close. And I have it now here. It's always a matter of getting the i's right, but anyway, I've written it for you last time. It's minus I del by del theta plus I sigma mu theta dagger del mu. So you see there is a translation in theta and a term involving translation in x mu. But this is not a constant translation, it's a theta translation. The point is that this is how f is going to transform under supersymmetry. Okay? But if we constrain it by this, then it's up to us to check that after transforming it under supersymmetry, the constraint still holds. If the constraint doesn't hold, then this constraint is too naive. It fails to commute with supersymmetry. Okay? Or maybe we should have said it fails to anticommute with supersymmetry, because this is an anticommuting derivative. So is Q. Q is also an intrinsically anticommuting, first order in theta kind of object. So what we see is that our constraint, if you like, our constraint operator del by del theta dagger fails to commute to anti-commute with Q and Q dagger. Is that obvious? Here's Q, here's del by del theta dagger. What will I get if I anti-commute them? What term am I going to pick up? I'm going to pick up this term, right? Because this will differentiate that theta dagger. And so I'll pick up something, whatever that thing is, doesn't look like it's going to be 0 on the field. So I've shown that these things fail to anti-commute. Okay. So therefore, the constraint was not supercovariant. So it's our job to find a better constraint which will be as useful as this one, but which is supercovariant. And to do that, we notice a very cute fact, which is that if we define an operator dA, again a spinorial differential operator, and what I'll do is I'll take Q, which has these two terms, and I'll just define D to be the same thing with a minus sign in the middle instead of a plus sign. So del A, which means del by del theta A, this is better, minus I sigma mu theta dagger A del mu. I could have, if I wanted, put an overall I outside everything, but for some reason DGR don't do that, and it doesn't matter because I'm going to use this operator mostly to impose a constraint. Okay, with Q, the factor of I is the same factor of I we put in when we talk about P mu being I del mu. It makes it omission because del changes sign because of partial integration from the in to the out, from the bra to the ket, if you like, and I restores the sign. So D will be anti-omission in that sense, but so what? So here's a D, and there's also a D dagger, which will be obtained by taking whatever we used to have for Q dagger, and again reversing a sign. So it's minus sometimes it's not worth writing these indices, and besides I think it's important for you to figure them out yourselves. So it's D dagger plus I theta sigma. You should practice filling in indices wherever I don't write them. Besides, they are all very, very explicitly given in the textbook of DGR. Okay. Now, why did we do this? It's pretty easy to see why this suits our purpose. This is very much like Q. Okay, and you remember that Q anti-commuted with Q dagger gave 2 sigma mu del mu, 2I sigma mu del mu. That 2 came because the first term in one Q and the second term in Q dagger and the other way around added up and gave me a 2. But now I have cleverly flipped a sign. Instead of adding, they'll cancel and give me a 0. So the claim is that the anti-commutator of any D with Q, so D with Q or D with Q dagger or D dagger with Q or D dagger with Q dagger are all 0. So I found an operator D which starts out being a derivative in theta, but it has a correction term, so very much like a covariant derivative. Well, maybe not very much, because we are used to the correction term being a function, but here the correction term is itself a derivative operator. So both are derivative operators. But whatever it is, it has the beautiful property that it anticommutes with all Q's and Q daggers. Okay, and you should check this. This being so I gave you the rough reason, but you don't have to care about the reason. Just take this, multiply them in one order, multiply in the other order, add, and you get 0. Okay, these calculations are all mindlessly simple, but you must do them. You'll never learn supersymmetry if you just go home from here and forget about these things, because the formulae can get very confusing later, and it's very important for you to work out these things yourselves. Okay. So having done this, we realize that constraining a superfield that, let's say, D dagger A dot on F equals 0 is a covariant constraint. What's less clear is whether this will also help us cut down the degrees of freedom the way we want. Of course, it should cut down something because it's a constraint. A general F certainly doesn't satisfy this. But what is the consequence of this, we'll explore in a moment. So it's a covariant constraint because if F satisfies it, then after I transform F with supersymmetry, the new F will still satisfy it. Okay? So, definition, a superfield. So now I'll introduce a more standard terminology, phi, capital Phi, that satisfies D dagger on phi equals 0 is called chiral. Okay. I've given the name phi to it, earlier it was F. Okay, so F will be rarely used and it represents the most general unconstrained superfield. Phi represents a very naturally constrained superfield. And its conjugate, its complex conjugate, phi dagger, satisfies the conjugate equation and is called anticommute. Good. Any questions so far? Okay. Now the next question is, how do we solve this constraint? Namely, what are the characteristics of a field which is constrained by this? Okay, so we need to solve the constraint, and that is actually rendered very simple by one observation. So we notice that a new shifted coordinate y mu, which is actually x mu minus I theta sigma mu theta dagger, exactly, satisfies d dagger A dot of y mu is 0. Can you see why? D dagger is defined out there. So can you see what's going on?
The del dagger will remove the theta dagger from here and will cancel the second term.
Thank you. So this contains a del dagger that's going to kill this fellow and leave behind theta sigma mu. The other term in D dagger, which is this, is going to differentiate x and leave behind theta sigma mu, and hopefully the two will add in the right way and cancel. Okay, so there's a complex sort of coordinate x mu minus I theta sigma mu theta dagger, which is annihilated by d dagger. Okay, it's just an observation, and there's a complex conjugate statement, which is that y dagger, y mu dagger, which is defined to be x mu plus I theta sigma mu theta dagger, satisfies d on y mu dagger equals 0. This is the complex conjugate statement. I hope you are beginning to get the feeling now, which will last throughout this course, that in supersymmetry everybody is naturally complex because the thetas are naturally complex. So almost every equation in normal life has a kind of doubling in supersymmetry because there's a complex equation and it's complex conjugate. But as I told you in the first lecture, these are dependent equations. So this equation is simply the complex conjugate of that equation, not an independent equation. But there are two natural y's, y with this shift, x with this shift with a minus sign, and x with this shift with a plus sign. Okay. So how can we use this to solve the constraint? Well, we claim that if d dagger on phi is equal to 0, then phi is a function of y mu and theta, but not independently of theta dagger. Okay. That's because the constraining operator d dagger has two possible. When it acts on phi, it's going to act on these two arguments. When it acts on this argument, it gives 0. When it acts on this argument, the only thing that acts is d by d theta dagger, so that also gives 0. Okay, because d dagger is a combination of d by d theta dagger and del mu. Okay, so in this way we've solved the constraint, and for the anti-chiral superfield, as we would expect, phi dagger is a function of y dagger and theta dagger, but not theta independent. So notice that the chiral superfield depends on theta dagger, but only through y. So what we've been able to do, instead of eliminate the dependence on theta dagger, which we would have liked, but which was not supercovariant, we managed to package the dependence on theta dagger into a dependence only on the coordinate y mu, which differs from x mu by a shift. And we'll see later that in some but not all circumstances, I can shift away this piece. Sometimes I can, sometimes I can't. We'll see it very precisely. Okay? Good. So now we can do exactly what we were hoping to do earlier. We can simply take the chiral superfield phi of y and theta and write it as phi of y plus root 2 theta of psi of y plus theta theta f of y. Do I have a half in the last one? No. Good. And we're sort of concealing something here, because although this is the expansion in theta, it's the expansion at fixed y, but y is not an ordinary coordinate, y is this combination. Okay, but we'll see that this is nevertheless a good way, useful way to think about this. In fact, we can see that right away, because now if I insert that y is this, then I can expand out phi, psi and f as functions of x and theta, and I'll get a few more terms, but I won't get any more fields in this theory. Okay? The independent fields are phi, psi and f. There are no more independent fields. If I expand out these as functions of y, I'll get these coefficients times derivatives of the original fields. Okay? So we have indeed achieved that the only independent fields in a chiral superfield are phi, psi and f. Moreover, we have a nice way to recover them from the original chiral superfield. if I want to find phi of x, all I have to do is take the chiral superfield of y and theta and set theta and theta dagger to 0. Okay, in that case, you see that in this expansion, first of all, I managed to set all these terms to 0. Secondly, I managed to set y to be equal to x from this equation. Okay. Likewise, psi can be extracted from this by first taking this covariant, supercovariant derivative dA on phi and then setting theta and theta dagger equals 0. So at the end, when we set theta and theta dagger equals 0, we are always going to be setting y equals x. So at the end, I recover the field as a function of the ordinary coordinate. And finally, f of x is 1/4 d. Sorry, I sometimes write it as script d and sometimes as cap d. It hardly matters. So it's 1/4 dd, but when you see dd, you should realize that it's one raised and one lowered, and it has the convention that I told you, which I think in this case is first one up and second one down from rotation. Okay, so we can recover the fields from the superfield by covariant procedures. Good.
Sorry, so
Yes.
what happened to that factor of root 2 for
Yeah, for psi, that's a very good question. And I don't know the answer. Excellent, I do know the answer. I copied the formula wrong from my notes. Thank you. It is important in the sense that to the extent possible, we'll try to keep all factors and signs correct in this course. Thank you. Okay. Now, something that the textbooks will rarely tell you, but I find infinitely useful, is that we can apply dimensional analysis to this system of superspace to get insights into what's going to happen even before we start to do anything. Okay. Now, we know that in four-dimensional Lagrangians, a scalar field has canonical dimension 1 and a spinor field has canonical dimension 3/2. Okay. Therefore, just from this expansion, I'd be inclined to guess that theta has a canonical dimension -1/2. But in fact, I argued that for you last time because look at this formula. This already shows me that theta must have -1/2 so that it can be added to x. This in turn comes from the supersymmetry transformations, okay, in which x transformed to x plus theta del by del x. That formula already shows you that the dimension of theta is -1/2. So that fact is pretty obvious. But from there come all kinds of nice things. So let's just do some canonical dimensions. Theta is -1/2. If theta is -1/2, this is 3/2, so that works fine. But look at this term, -1/2. The whole thing is +1. So the canonical dimension of f must be 2. Okay. Therefore, the canonical dimension of f is 2. Okay. Now, the first thing that we would like to do with the superfield is to write kinetic terms. As you know, kinetic terms are by definition dimensionless in 4 dimensions. Okay. The dimensionless nature comes from the fact that this has dimension 1. So del mu phi, if I add the dimensions of del and phi, adds up to 4. Okay. This has dimension 3/2. So psi del psi, if I add it all up, comes to 4. This has dimension 2. So the unique quadratic term I can imagine writing is f squared. Therefore, the only quadratic term in f of dimension 4 is f squared. By f squared, and this is a little generic, it will actually be f star because these are all complex. Okay, but I mean f squared. So this gives us confidence that f is not going to be a dynamical field. Because a dynamical field in field theory needs a propagator, and the propagator of f is basically 1. Another way to say is that in the functional integral of the field theory we are going to get, if f has a kinetic term just f squared, then it's a pure Gaussian integral, It's not determinant of the kinetic term operator, del squared or anything, it's just some number. So it will be trivial and can be eliminated. So such fields are called auxiliary fields. And they occur everywhere in supersymmetry for reasons that we'll explain hopefully at some point. This is mere anticipation. It's actually possible and we're just going to do it to show you precisely this and lots of other stuff. Okay. So one more consequence of dimensional analysis will be useful. But for that, first we have to define what we mean by a superspace action. Okay, so in ordinary field theory, in ordinary space, an action S is the integral d for x of L, and then the fields, L is a function of fields and the fields depend on x. So it's natural to assume that in superspace, S is equal to d for x, d2 theta dagger of some L, which depends on superfields, which themselves depend on x theta and theta dagger. Okay. However, the puzzle is we don't really know what integral of d2 theta and d2 theta dagger mean. We know how to integrate in x, at least in principle, but in theta and theta dagger, it remains a bit of a mystery, and we are now going to show that the answer for integral in theta and theta dagger is essentially unique with some very, very simple assumptions. But even before we do that, we anticipate this form. However, there's a small puzzle if this Lagrangian, let's say, depends only on phi and not on phi dagger. Okay, the Lagrangian can depend on both phi and phi dagger, but some of its terms might depend, let's say, only on phi and not phi dagger. Okay. In that case, it would not make much sense to integrate in theta dagger because this thing wouldn't depend on theta dagger effectively. And so actually, we turn out to have two types of actions in superspace. This I'll write a subscript d for d term, which is a conventional term for such an action. Here L means some term in the Lagrangian. It need not be the whole Lagrangian because I get the action by integrating each term in the Lagrangian, term by term. Okay. The f term contribution would be integral d for x d2 theta L of only phi. Okay, but then plus complex conjugate. See, phi is intrinsically complex because it satisfies that complex constraint. D on phi, d dagger on phi is 0. So, if I had a term involving only phi, then I must add to it the corresponding complex conjugate term involving only phi dagger. And that will be d for x, d2 theta dagger, L star of phi dagger. Okay. In these kind of considerations, I am not being very careful with my notation because I want you to think what it means. Okay. So you shouldn't come back and say, what did you mean? This is L or this is L, which of these is the Lagrangian? I'm talking term by term in the full Lagrangian. Whenever the term depends on both phi and phi dagger, we must integrate it in theta and theta dagger. But we've seen that there's a consistent constraint which eliminates the theta daggers. And therefore, when such a term occurs, which only involves phi, which only depends on theta effectively, then I would only integrate in theta. Okay, this is already some general consideration independent of what my definition is of this integral. Okay, and one more thing that you will see right away, you might be worried saying, well, look, phi, if it's a chiral superfield, it depends on y and theta. Okay. But y depends on theta dagger. So how come we're not integrating in theta dagger? Because actually y depends on theta dagger. And what's the answer to that? Very beautiful and simple answer, which is staring you in the face now.
The Jacobian for difference and temporal y will be the same.
Yeah, but that's not enough. Jacobian is a change of variables, but why am I allowed to make that change of variables without any cost?
Jacobian 1.
The Jacobian is 1 indeed, but that means that I still have to take this y and shift it to get back x, right? But what allows me to shift it? That's right. This thing is under integral d for x. Okay, so integral d for x, a function of y, is the same as integral d for x, the function of x. Okay, so note, we can shift y back to x under the integral sign. What does it mean in practice? What are we losing something, or this is a general thing we can always do? When we say we can shift something under an integral sign, it means we are losing what?
Range. The range.
No, the range is infinite, I assume. I'm not worried about the range, but it's the same thing as range, what you're saying. We are losing total derivative terms. So this is not an exactly true statement that y can be shifted to x. Okay, so even though the Jacobian is 1, okay, what it really means is that when I evaluate the function of y, there would have been some total derivative terms which would have gone away, leaving behind the original function only evaluated on x. And we saw that because you remember, I made the expansion of the superfield in component fields of y, and then I said we could further expand those component fields as functions of x by taking out these theta dagger terms. But all those would be total derivative terms. Okay? So, losing total derivative terms. Yeah, what's the question?
I mean, those extra terms wouldn't they be killed by the two-theta?
Yeah, so the point that we are worrying about is that why are we justified in not putting d2 theta dagger? Okay, so of course it's true that they would be, well, first of all, they wouldn't be necessarily killed. For example, if I take this and I expand to second order and theta dagger, I would have two thetas and two theta daggers. Then d2 theta would eat up the two thetas.
So you would be left
with two theta daggers. And I emphasize all these considerations are independent of knowing actually how to do the integral. Any sensible integral, when performed, should leave behind a result independent of that variable because it's a definite integral. Okay? Integral dx of something is no longer a function of x. Integral d theta of something is no longer a function of theta. Okay. So the worry was that since y depends on theta dagger, even after expanding this and integrating in theta, I might be left with something depending on theta dagger. In which case my prescription not to integrate in theta dagger would have been faulty. But it scrapes through because all such terms are annihilated by the integral of d over d for x because they are all total derivative terms, and therefore this is actually the correct prescription.
So we assume the field to vanish actually.
Yeah. So here, of course, boundary conditions are all important, and there's a general rule that in supersymmetry, if you just put everything on in a periodic box with periodic boundary conditions, then you're okay. That's easy to do in space. It's not so easy to do in time because it has a physical implication. So there are all these implications in supersymmetry theory, the boundary conditions. But if we just assume that fields die off at spatial infinity very fast, fast enough to kill any integral of a total derivative, then we are fine. Okay. Now I'm about to tell you how to perform integrals in theta, but first I just want to stress this fact that in both these prescriptions, one of which has d for x, d2 theta dagger of a Lagrangian involving chiral and antichiral superfields, or just integral d for x d2 theta of a Lagrangian involving only chiral superfields and then plus its complex conjugate, which is the antichiral part. Okay. In both these prescriptions, one can imagine doing the theta part of the integral, and then you'll be left with something which, when integrated in x, gives me an action. So that thing that I'm left with after integrating out theta and theta dagger here or theta here is the ordinary space Lagrangian. Okay, so after integrating in theta dagger as appropriate, that is both of them here and only one of them here, we are left with ordinary space Lagrangians and this once more reaffirms something that we suspected from the beginning, that all this superspace is all about packaging some number of ordinary space fields Yes.
Just one, this shift in x, I
Yes.
mean, since the correction term is complex in general, it's not just shifting on the real axis but
No,
also.
no, no. Oh, I see.
So probably it's okay because L doesn't have any poles or anything.
No, I think that's not the reason it's okay. I think the reason it's okay is that you can put this inside a bracket and add the complex conjugate
Okay.
and keep all the total derivative terms on both, and then I'm sure that will be okay. Oh, actually, maybe I'm wrong. I think you're right. I think you're actually right. And the reason is that while this will depend on y, that will depend on y dagger. So the shifts are actually opposite. You're quite right. I think that's a good observation. Aninda is pointing out that in doing this shift from y back to x, we are really shifting x by an imaginary piece, I theta sigma mu theta dagger. But I'm not sure it's imaginary.
For some
Yeah, it is imaginary. It is imaginary. Yeah, that's correct. It's imaginary. That's why y, the dagger of y is a different quantity y dagger. It has to be imaginary. And you have to do that one shift here and the opposite shift in the complex quantity. That's correct. You should worry actually even more because right from the beginning when we said y is x minus I theta sigma mu theta dagger, or even earlier when we said that, in fact why this, when we said that under supersymmetry delta x mu is something like I epsilon sigma mu theta dagger plus the complex conjugate, this is very worrying because x are four independent Euclidean coordinates which are real numbers and we are shifting them by a piece which is not a real number but it's a product of two anticommuting numbers epsilon and theta. So for example this shift, if I took a very high power of it, I'd get 0. Okay, although it's commuting, so it's legitimate to add it to x, it commutes because it has two spinors. But we should keep in mind that the product of two spinors, although commuting, has a memory of its anti-commuting nature because if I raise it to a very high power, I get 0. Once I've used up all the spinors in my theory, I get 0. Okay, so this is a kind of tricky thing about supersymmetry, but the sensible way to think of it is that these are all so-called Grassmann numbers, some special type of numbers, and a basic commuting quantity like x, like a coordinate, has sort of a value in a base and then there's a fibered space where we take the base values are the conventional values and then we add values in the fiber which are anti-commuting. And you can make a kind of, you can define a supermanifold which has fairly sense.
I mean, this L does not have those high powers and it's integrated over theta, so that
Yes,
will probably...
that's correct. That is correct.
So it's not really like analyticity in which delta x mu has a little bit of y. Some imaginary part is added. It's rather is imaginary, but in the super direction.
Yeah, it's imaginary in the super direction.
Yeah, so it's not even shifting of contour. I mean,
Probably that's correct. I think that's correct. It's not, that's good. I think that resolves the question.
Yeah,
It's neither real nor imaginary in the base. It's imaginary but in the fiber.
That's right.
And in the fiber, whether you're real or imaginary hardly matters, and you're basically shifting the commuting part by a Grassmann part, although Grassmann even. Grassmann is the name given to these anti-commuting numbers, but also to the full algebra they form. So product of two of them is also Grassmann. Okay? And that's what Gautam was saying. And in fact, the supermanifold people, I think, they started calling the base as body and the fiber as soul and all those things. So there's a whole literature on body and soul stuff.
Certain time inhibitions in the section.
Yes.
Yeah.
That's right. That's right. And then we would have to think of this whole measure as some kind of measure on the supermanifold and so on. So, but this is taking us in directions far too close to my soul for comfort. So let's get back to mere bodily things. This is the point I was trying to stress, that superspace is turning out again to be only a clever packaging of information that we could in principle have obtained otherwise. Okay? Because after all this stuff, what we'll be left with when we finish integrating out d2 theta from here and this d2 theta dagger here are things which are functions only of x because we've integrated out their theta dependence. And then once they're functions of x and their integral is an action, then it's fair to call those functions of x a Lagrangian. Okay? Now, you can do that very generally. You can always imagine integrating out a few coordinates and having a Lagrangian depending on the remaining ones. But the crucial thing that goes wrong in field theory, if I try to integrate out one coordinate at my will, is that the remaining theory will be non-local. Okay, but here, because theta are anti-commuting coordinates and the expansion of the field terminates, there is no non-locality. So let's do it. So now we have to grapple with the fundamental question: what is integral d theta?
So the term can be written like f term.
That's also true. The d term can be written like an f term, and then after integration, we can first integrate out this, then it will be a function only of theta, then we integrate out this, then it's a function only of x. Okay, we'll see that all these things, as long as we do them right, these are all consistent procedures. Okay. But there are different definite consequences which are different for these two terms. Okay, so how to integrate in theta? I don't think there's any way to prove what you should do, but for that matter, even in ordinary space, you define an integration and then it's not so much proving the formula as finding out what it's useful for, to give some kind of first principles definition. And here we are going to do that by just examining a toy example and requiring some basic physical properties or mathematical properties to hold. So the toy example has a very small superspace with two coordinates t and theta, both real. One commuting coordinate and one anti-commuting coordinate, both real. Just a toy example to think about functions on it. Okay. So a superfield f of t and theta can be written as one ordinary function of t plus theta times another ordinary function of t, and that's the end of its expansion in theta. There's only one real theta, so there are no more terms. Is that clear? Okay. Now the question is, what is integral d theta f of t and theta? Okay. Now we have in mind a definite integral, and in fact in this context, indefinite integrals really don't seem to make sense. Indefinite integral means some integral plus constant, or even an integral with limits. Okay, we are really looking for the analog of integral from minus to plus infinity, because when we write field theory actions, this one is integrated from minus to plus infinity. Okay, and so what we'll do is we'll be looking for an integral which doesn't require the specification of limits, which means over the whole range of Grassmann numbers, whatever that means. Okay, so that's the first thing. I don't have to put limits here. Okay. Now, integration is linear. So I'm assuming that the theta integration has the same linearity property of ordinary integration. Therefore, integral d theta of f of t and theta is the same as integral d theta of f of t plus theta g of t. This is of course trivially true. Linearity property tells me that this is f of t times integral d theta of 1 plus g of t times integral d theta of theta. Probably this is minus. We should keep in mind that the order is important. So if theta is anti-commuting, g will also be anti-commuting.
Because theta and g.
It crosses theta and d theta. Thank you. Okay. Good. For this argument, actually, thank you. I think that's a lot better. Okay. Good. So this is the answer. Okay. And therefore, if we know integral d theta of 1, which is like the volume of the whole space, and integral d theta of theta, then we know integral d theta of anything. There are only two integrals that I need to specify, and then integral d theta over any function is known. Is that clear? Okay. So for this I use linearity of the integration. The next property I am going to use is invariance under a shift. So we assume that integral d theta of theta is the same as integral d of theta plus epsilon of theta plus epsilon. Okay? Because here I have just taken a shifted way. First I have renamed this as theta prime, which I can do, and then I write theta prime as theta plus epsilon. So I have this. The only thing this could be doing is changing the limits, but since in my assumption there are no limits, this is fine. Okay. The next assumption is that d of theta plus epsilon is of course the same as d of theta. This is normal, because if I shift something by a constant, the measure doesn't change. So it's this. Now I use linearity again, and I get d theta of theta plus epsilon times d theta of 1. Alright. Makes really no difference for us. Good. Okay? Fine. So from this it follows that integral d theta of 1 must be 0. Okay? That leaves only integral d theta of theta, and that can be fixed as a normalization. It's a definite answer. It shouldn't be 0, otherwise integral of everything will be 0. So we just choose it to be 1. Okay, so integral d theta of 1, this 1 need not have been put in. Integral d theta is 0. Integral d theta of a theta independent quantity is 0. While integral d theta of theta itself is 1. Okay, now I had one real theta, but if I extend this to two complex thetas, nothing really changes. Okay, I just have to break up the measure into the product of the individual measure over each theta and the function into its components by expanding out in theta, and then each time I use these two rules for each theta independently. And the only thing that I have to worry about is the sign, because things will keep anti-commuting across each other, but that's a detail. This defines the integration over any number of thetas. And just to be sure that we understand what it is, so integral d theta 1 of theta 1 is 1, and integral d, now this 1 is theta 1, theta 2, theta 1 dot, theta 2 dot. Okay, integral d theta 1 of any of theta 1 of theta 2, theta 1 dot dagger, theta 2 dot dagger are all 0. Okay, because the independent variables are theta 1, theta 2, theta 1 dot, theta 2 dot. Okay, so these three are independent of theta 1, so they can all be taken out of the integral sign and I get 0. Then I use this one to get 0. Okay, if you find this unconvincing because these thetas are complex, you are free to work out the rules with real thetas. Just take theta 1 plus theta 1 dot dagger, give it some other name. In that way you will manufacture 4 real thetas, then implement these rules on the 4 real thetas which you can't argue with, and then get back the rules for the complex thetas. You will just find the same answer. There was a question? There was some question. So this defines integration over thetas. It's called Derivation integration. It's indeed very novel and very impressive. By the way, this is not the first time that we encounter it. If you do ordinary field theory with fermions and you do the path integral, you will be doing Derivation integration there. So it's not tied to supersymmetry in any way. We are just using something that if you had all done field theory with fermions carefully, you would have already seen, which means actually that you've already seen it. But most books just tell you that's a rule, and I've just tried to argue that it's not so much a rule, but it's the only consistency we can find. And most important, that if you sort out the issue with one real variable of each kind, that's more than enough. You've got all the information you need for multiple variables. Okay.
If we are free to fix this normalization,
Yeah.
so we could have in general terms like say theta 1, theta 2.
Yes.
So in that case, the integral over both theta 1 and
I see.
theta 2 would give me a square.
Yes, that's true.
So there could be another term which is having just theta 1.
Yes.
So you will be having a square into some function plus a into the other function. So it's not an overall normalization.
Actually, it still is. It's not an overall normalization in the sense it could occur in all your formulas. But then all the quantities that you work with, like Lagrangians and all, would also have a and a squared appearing all over the place exactly to cancel that out. So that's something you can try to check. Just imagine that you choose such an A and try to see whether you can, all these formulae that I'm giving you get messed up. They will get messed up. Then try to see if you can correct the formulae by changing the superspace action. Okay. It might be that the D term action has to be divided by A squared and the other one has to be divided by A or maybe to the fourth, whatever it is. It can always be another. Okay. Good. Now comes some fun. Finally, we've got out of the way all the formal stuff. And now we can examine what is lying inside these chiral superfields phi and see that superspace has done the work we want. So recall that, so now let's look for quadratic superspace actions. Why quadratic? Because we know from ordinary field theory that there are two types of quadratic terms that occur for a normal field. One is called the kinetic term, one is called the mass term. And if those are the only terms, then it's called free field theory. And if there are any higher order nonlinear terms, then it's called interacting field theory. So let's understand free field theory before we put interactions in. Okay. Now we've seen that superspace actions can be of two types. First of all, let's notice that, and let's do this with only one chiral superfield phi, and its complex conjugate phi diagonal. Okay, so this capital Phi will always be chiral. I won't always be specifying that. Okay, so there are two ways I can make quadratic terms out of this. One is to take phi times phi dagger. Notice that when I multiply phi with phi dagger, the result is no longer a chiral superfield, nor an anti-chiral superfield. Okay, that's because if I act with D dagger, that will annihilate this but not that. If I act with D, that will annihilate this but not that. So it doesn't have any chiral constraint. Okay, that and therefore in particular it depends on x theta and theta dagger all in an essential way. So I must integrate this in d2 theta dagger, and of course lastly in x. So this is a D term. I'll explain later why I call it D term, but I said that T is the label I give to anything involving integral over all the thetas and theta daggers. Okay. What's the other independent quadratic term I can make from phi and phi dagger? No, I just want to make a product. I could consider derivatives, but right now I just want to take powers. So if I have a complex variable z and z bar, phi d square theta phi squared, quadratic term. So his point is that from phi I can make phi squared, which is different from phi dagger. I can also from phi dagger I can make phi dagger squared. And I notice that if I make phi squared, then this is chiral because phi was chiral. So this one is non-chiral. This one is chiral. Because if I put D dagger on this, I get 0 because whenever it acts on either of the phi's, I get 0. Okay, that means this needs to be integrated only in theta and then in d for x. Okay, and then I need to add the complex conjugate, which just for one time I'll write it out explicitly. And this is what I've called F term. Alright? Is that clear? And is the theorem clear that if I raise If I take any function of a chiral superfield, then it's chiral. If I take a function of the antichiral one, it's antichiral. But if I take a function of both phi and phi dagger, then it's neither chiral nor antichiral. I hope that part is very clear. Okay. And now there's almost nothing left to do except compute. But first, our favorite thing, dimensional analysis. Okay. So for dimensional analysis, let's notice that these are both supposed to be actions, which means after completing all the integrations, it should be dimensionless in units where the dimension of h bar is 1. Okay. This has dimension -4 in units where energy or momentum have +1, which is the dimensions we've been using all this time. Okay. What about d theta? Can you tell me the dimension of each d theta? Plus half. Who said plus half? Good. Plus half is correct because integral d theta times theta is 1. So if theta had -half, then integral d theta. So d theta must have plus half. By the way, you might have noticed that these rules, integral d theta of 1 and theta, which I gave you, tell me that integration and differentiation are the same thing in these numbers. Okay, this is just a comment. D theta equals 1, which is the same as del by del theta of theta, and d theta 1 equals 0 is the same as del by del theta of 1. So integration and differentiation are the same. And that's another way of saying that the canonical dimension of this measure is opposite of the canonical dimension of theta, because it's really d by d theta. It's puzzling because in normal life, if x has a dimension, then dx should have the same dimension, here it has the opposite dimension. Good. So from that, we see -4 here and +2 here. Okay, so altogether -2. We know that phi has canonical dimension +1. So phi dagger has dimension +2. So this term is dimensionless without any coefficient. Okay? Dimensionless as it is. Because -4 plus 4 times half plus 2 equals 0. What about the lower term? What is its dimension? -1 is correct, because this is -4 plus 1, that's -3, then +2, so it's -1. That means it needs to be multiplied by a coefficient of dimension 1. Now in a free theory, the only dimensional coefficient around is the mass, and this teaches us that this is going to be a mass term and the coefficient should be m. Okay? While this one, having no coefficient, we expect it to be a kinetic term. These are not general rules, these are rules only for the quadratic part of the Lagrangian. There will be higher order terms in both of these. Those will be generalizations involving interaction. But for the quadratic term, we see that the kinetic term is a d term and the mass term is an f term. We anticipate that just on dimensional terms. And now we'll do it and we'll see that our anticipation turns out true. Is that clear? So I hope you followed this logic. We just counted up the dimensions of this, found that it's already 0, and since this is quadratic, it can either be a kinetic term or a mass term, but if it has dimension 0, it must be a kinetic term. We did the same thing here, we found that its coefficient must have dimension +1, and therefore this is naturally to be thought of as a mass term, but interestingly, it's m and not m squared which appears in front. Okay? If theta hadn't been in the picture and this was a scalar field, we'd have put m squared, phi squared. The mass term looks very similar to a scalar mass term, phi squared, but it doesn't come with m squared, it comes with m in superspace.
So So the argument is that you find some dimensionful coupling,
Yeah.
and therefore there is a scale, and what else can it be then mass?
At the quadratic level, that's the only thing it can be, because we are mentally attuned to the fact that in field theory, the quadratic Lagrangian has the physical interpretation of kinetic term and mass term and no other.
So that is why the fact that the dimension is 1 doesn't bother us.
Yeah, I mean it's a quadratic term, so the quadratic term already shouldn't bother us, whatever its dimension. If the coefficient had negative dimension, it would have been quite alarming. But as we see, it has positive dimension 1. And we see some nice feature of supersymmetry without doing any work. We see the coefficient has to be a mass and not a mass square. And so although this is some kind of bosonic field, the fact that m and not m square comes in somehow reminiscent of fermions. So the superfields have a little bit both the properties, and we'll see exactly how it works out now. I'm doing all these things to motivate you to remember what's going on, because these are the ways that you remember what's happening. But then we do the actual calculation and you'll see for yourself that everything I'm saying will turn out true. You need not, if you have any doubt about this reasoning, you don't need it. Okay, so with that, let's start. And now I'm going to be a bit fast because it's really important for you to check all these things on your own. I'm just going to quote quickly what you get when you do this. So, so integral d2 theta of phi square is the first thing you want to do. We do the f term first. Integral d2 theta of phi square. This is equal to integral d2 theta of phi plus root 2 theta psi plus theta theta f, the whole thing squared. Now we must remember that these were functions of y, but in an f term, since there's only functions of y, there are no functions of y diagonal in this, because this is a chiral and not anti-chiral superfield. So we can shift y back to x. So y goes back to x. We just do it on the way and forget about it. We better not make the same mistake when we are doing d terms. In d terms, there will be a dependence on y and y dagger, and we can't possibly shift both of them away because they are opposite of each other. Okay. The next thing we notice is that when we expand out this, its final goal is to be integrated in d2 theta. Okay. That will be non-zero only if I keep the term from squaring this, which is quadratic in theta. I can't keep any term higher than quadratic in theta because those will be 0, and I can't keep any term lower than quadratic in theta because then one of these integrals will not have a theta there, and I'll have to use integral d theta of 1 equals 0, and that term will be 0. So for all practical purposes, this is the same as d2 theta of so phi f comes twice, this times this, and so 2 phi f theta theta plus 2 theta psi theta psi. Okay, you have to remember how the contractions are. If two spinors are sitting next to each other, then it's one up, one down. I always forget, I think this way, similarly here, similarly here. Okay? So that's all I need to keep. Good. Now, the next thing is a very simple exercise. And this one I want people to do, and I'm going to ask somebody at random next time to come here and do it. Is that theta psi is the same as minus a half theta psi. How would I prove such an identity? Explicitly right, thank you. There's nothing like it when there are two components in your objects, okay? You just write this as theta upper 1 psi lower 1 plus theta upper 2 psi lower 2. Next, the same thing. Next, you notice that many of the products are 0 because they have theta 1 on both. You only need the one where you get theta 1 here and theta 2 from there, and psi 1 from here and psi 2 from there. See how many times it comes, write down the answer. Repeat the process here, write down the answer, compare the answers. That's it. Okay. So with this use of that formula, this becomes d2 theta times theta theta times 2 phi f minus psi psi. Okay. Now the last step is we have to figure out what is d2 theta. What is the meaning of d2 theta? See, we have normalized each d theta, but you know that in complex analysis d2z is not dx dy. It's really dz bar, sometimes over 2, sometimes over root 2, whatever. And what we are going to do following DGR is that we want d2 theta 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 to be 1, so that every time we have an integral like this, we'll just be able to put it to be 1. Okay. From this it follows that d2 theta means a half d theta 1 d theta 2. Okay. To check this, you need to show that theta theta, when expanded out, is minus twice theta 2 theta 1, which is a true statement, I hope. Yeah. No, sorry, plus twice.
Yeah.
Twice theta 2 theta 1 or minus twice theta 1 theta 2. Okay. Again, because there are hidden spinor indices and you have to add up over all of them. With these two things, you see that we are through because half will cancel 2. D theta 2 will integrate theta 2, go out of the situation, and then d theta 1 will integrate theta 1, go out. So there are no more minus signs. Okay, so this is a definition. But the useful thing is that, and from there it follows that the F term action, F term contribution to the action, d2 theta phi square is equal to, so this is 1, so we are only left with 2 phi f minus psi psi, and we must not forget that there is another term d2 theta dagger phi dagger square, which is clearly going to be 2 phi star f star minus psi dagger psi dagger. Okay. I use star on scalar fields because it's ordinary complex conjugate. Actually, this dagger is also the ordinary complex conjugate term by term, but it's on a 2-component problem. Okay. And now you can see right away, though I'm not going to do this now, but I'll do it next time. You can see that what we want in front is a half m in my conventions, a half m or m, I'm never sure. I don't remember what I think. Yeah, for a while spin, I think it's half m. Okay, so that this becomes minus a half m psi psi plus m psi dagger. We'll do that next time. Okay, we see that we have got some fermion mass term. This looks a little weird. Okay, but the story is not going to be complete until we do the d term. I don't know if I have time for that right now. D term is a bit lengthy. Yeah. Well, you know, yeah. Let me make the correct statement next time. Probably, yeah, that's probably great. Good. So I will do the D term next time, and next time also we'll complete our review of supersymmetry at this level. It's taken 3 lectures altogether, but I hope it's worthwhile because we can't really do MSSM unless we all are clear about these details. And so besides the D term, I'll show you next time that there's another constraint on superfields different from the chiral constraint, and that's merely the constraint that it's real. Real also cuts down its components, not so drastically but quite a lot. And we'll see that supersymmetric theories involving vector fields are embodied in those kind of superfields, and so the real superfields are called vector superfields. So next time we'll do D term. What this means to do D term is that we'll be evaluating d2 theta dagger phi. Okay. The second thing we'll do is to define vector superfields and see how gauge invariance fits in. Because clearly if we are going to do the MSSM, then we need a theory that's both supersymmetric and gauge invariant. because it's going to be an extension of the standard model, so it better have SU3 cross SU2 left cross U1 in it. Okay? So we do that, and that will be enough preparation, and then from the lecture after that, we'll start on the MSS. Are there any questions?
The superfield you always take it to be commuting.
Not necessarily. We'll see that next time, that sometimes it's natural to take it to the anticommute. Actually, I can even give you an example from what we know. If you take a chiral superfield, if phi is chiral, then d dagger a dot on phi is 0, but let's consider dA on the same field phi. That's not 0, right? Okay, but it's still a superfield because phi had an expansion in thetas. After doing this dA on it, it's a new thing with expansion in thetas. But now it's got one spinor index. So this is a spinorial superfield. What you probably meant is that this is not a fundamental field. This is obtained from a fundamental scalar superfield. So the question is, are all our superfields going to be fundamentally scalar superfields? And even that basically is no. We'll see that.
And what I was asking is rather that if there's something like a spin matrix, that if you have a scalar thing, you have to, it should be commuting.
Yes. So the question is, okay. Yes, I think that is correct. There is spin statistics, and for a very simple reason, take any superfield and put all its thetas to 0. Then it reduces to its first component. The first component will be an ordinary field, okay, which will obey spin statistics. Therefore, the superfield should obey the same spin statistics. Thank you. I hadn't thought of this, but I think that's the answer to your question. Okay, thanks.